This is the one-way analysis of variance video on visualization. There are two overlapping ways to think about the inputs into an analysis of variance. One way to conceptualize things is that you're fundamentally assessing the validity of its assumptions. Another way is to think of things as that you're first and foremost trying to visualize the data. Although both ways of thinking are useful, visualizing the data is the more empowering, so that's the approach we'll take here. Before proceeding to data visualization, let's spend a few moments from the perspective of checking modeling assumptions, for no other reason than this is a concept that you'll encounter when reading the literature. This way of thinking treats a statistical analysis like a protocol, not essentially different from a protocol used to perform a laboratory experiment. Following this statistical protocol, you're asked to check two things. First, is the distribution within the data within each group approximately normal? And second, are the variances of the groups to be compared approximately equal? Although a reasonable way of thinking about things, this protocol-based approach does have a danger, namely that you have to decide what to do when the assumptions aren't precisely met, which unfortunately is most of the time. When model assumptions aren't precisely met, you're left with the task of determining whether the problem is large or small, large being interpreted as causing the results of the standard statistical analysis into doubt, small being interpreted as not. In other words, in practice, the analytical protocol is not nearly as precise as it appears on paper. Moreover, having to call a statistician every time you make these decisions isn't consistent with our goal of empowering you as much as possible. Accordingly, in general, we won't talk about assessing the validity of assumptions, but instead we'll apply the second way of thinking, which is to visualize the data. The visualization exercise for the one-way ANOVA is essentially the same as for the t-test. Create box plots for each of the groups. Determine whether the group means are fair representations of the centers of their distributions. You need all of the groups to behave well in order to safely proceed. Well, what should you be looking for when you visualize the data? One of the things you should always be looking to do is identify and eliminate or fix impossible data values. For example, a BMI of 295 is almost certainly a 29.5 with a missing decimal point, and a BMI of 999 is almost certainly a code for a missing data value. FDA submissions require you to keep track of and justify every such modification to the original raw data. Even in less formal settings, it's good practice to do the same. One thing that's particularly helpful is to perform the data cleaning in a fashion that's blinded to study group. If you don't know which patients are which, you won't be in a position to bias the results through your data cleaning process. Importantly, you'll be able to reassure your audience of this fact. Same comment applies to the treatment of outliers. After dealing with the impossible data values, your next task is to identify those outliers that are so extreme as to cause the results of the ANOVA to be unrepresentative. Typically, the main impact of these outliers is to cause one or more means in the ANOVA to be unrepresentative. Using the example in the slide, with 10 patients per group, replacing a BMI of 29.5 with an incorrect value of 295 would cause the group mean to increase by approximately 26 points, and thus be inconsistent with the main body of the data points. A secondary impact of outliers is to increase the variability of the observations within the groups, which reduces statistical power, and that's discussed later. Another secondary impact of outliers is to make the distribution of the data depart from normality. Apart from checking for extreme values, whether impossibly extreme or merely outliers, you're also asked to visualize the shape of the data. Histograms are helpful, and R has some functions that smooth histograms to make them easier on the eyes. Normal probability plots can be used to assess normality, although this isn't always such a big deal. First, if the ANOVA is reasonably robust to most departures from normality. So in practice, if the graphical display doesn't jump out at you from the page, it probably isn't a problem. Second, for moderate to large data sets, the central limit theorem comes to your assistance. In plain English, the central limit theorem states that for any distribution, regardless of its shape, with sufficiently large sample sizes, the sampling distribution of its mean will be normal. Sampling distributions are covered in the video on hypothesis testing. Briefly, sampling distribution is a hypothetical concept, which is based on repeating the study in question a large number of times. Each replication of the study generates a new value of the means, which in turn become single data points within the sampling distribution. Statistical inference in the one-way ANOVA is based on the sampling distribution of the group means. Thus, as long as the sample size is large enough, normality-based theory will apply regardless of the shape of the data. The approach to normality for the sample means is very rapid when the underlying distribution is close to bell-shaped. Closer, the more the underlying distribution departs from normality. But as long as the data set's large enough, you'll get there in the end. With all this in mind, checking the shape of the data is particularly important for small to moderate-sized data sets. If the departure from the bell curve is sufficiently profound and the sample size particularly small, the central limit theorem won't apply, and statistical consultation is in order. One thing that a histogram is particularly helpful in showing is whether the data set has multiple modes. The ANOVA doesn't always perform well when the distributions in questions have multiple modes, the most typical case being bimodality. Apart from any statistical considerations, there's also the problem of interpretation. Multiple modes usually point to multiple subpopulations, but the one-way ANOVA is designed to compare groups that are homogeneous. If multiple subpopulations are present within the groups and can be reliably identified, then you should apply a more complex analysis that takes subpopulation into account. Another thing to check is whether the magnitude of the variability of the groups is roughly similar. For example, do the variances differ by more than a factor of 4, or equivalently do the standard deviations differ by a factor of 2? This doesn't require any plots, simply a review of a few numbers. The most dangerous situation is when the sample sizes vary and the smallest group also has the largest variance. In practice, differences in variability are often caused by either outliers or misscaling. We'll cover both of these soon. A final thing to check is the sample sizes within each group. One reason to do so is it reminds you to check for missing data. For example, if you studied 50 patients in a group, but your analysis only has 10 data points, this tells you that either something went haywire during the data management, or that the outcome variable was missing for 40 of these 50 patients. Another reason to check is that, in the same way that a chain is no stronger than its weakest link, a one-way ANOVA is no stronger than the size of its smallest group. This is a general principle that can often assist in study design. What you should do when things go wrong depends on what's gone wrong. The most likely things to go wrong are outliers and data that are out of shape. Considering outliers, let's discount the possibility that the data value in question is impossible, since we know what to do with it then. The problem is that an outlier can have both a disproportionate impact on the results and still be real. For example, most hospital stays associated with labor and delivery in the range of 1 to 4 days, but unfortunately things occasionally go badly wrong, and a 180-day stay represents reality. Here's some of the options. All are useful, none are perfect, and which to select often depends on the context. We can perform a sensitivity analysis with the outliers in and out. Even if it's hard to decide which of the two analyses is most appropriate, you will have at least demonstrated how much of an impact the outlier has on the conclusions. You can perform an sensitivity analysis with the outlier set to a less extreme value. In the labor and delivery example, you might change the 180-day stay to a 14-day one. This reflects the fact that the stay is long, which would be lost were the data point to be dropped, but prevents it from dominating the analysis. You can perform a non-parametric analysis of variance, either as a sensitivity analysis or the primary one. Many non-parametric tests proceed by transforming the data into ranks and then proceeding as usual. For example, for a data set with 100 points, the data would be transposed into integers from 1 to 100. The difference between the highest and second highest data point is simply the difference between 99 and 100, and no single data point can dominate the analysis. When data are out of shape, the problem usually is multiple modes or long tails. As noted previously, multiple modes usually mean multiple subpopulations, and this can be accommodated for by a more complex statistical analysis. Long tails can often look like outliers, as illustrated on the screen. Long tails often come from data that are proportional rather than additive. When this is the case, a long transformation is often sufficient to make the data better behaved. Here the key is to consider the underlying mechanism by which the data were generated.